So, hello everybody. My name is Simon Hofmann. I'm a doctoral researcher at Max Planck Institute for Human Cognitive and Brain Sciences in Leipzig, Germany. And I'm very happy to be invited to this very important and exciting symposium. And I hope I can contribute with some humble thoughts to this quite important topic. So my presentation is very much motivated by my own research, where I apply deep learning models for neuroimaging. And over the last years, I more and more thought about how to make actually these models more sustainable in the field. So in the sciences itself, more and more journal covers basically are featuring these model class under this umbrella term, also AI. But at the same time, there's also a lot of criticism claiming that this is more of an hype and that these models are purely data hungry and we can little learn from them. However, you cannot really reject the idea that these models also in the field of neuroimaging find many applications and turn out to be state of the art. For example, when you consider brain age predictions, Peng et al., for example, recently published a paper where they could show that they outperformed many competitors, even on the same data set, with their ensembles of convolutional networks. And even with little training data, they outperformed also linear models. But one big issue remains is that these models are highly complex with a huge parameter space, which gives them also often this label being a black box. So in my personal research, I'm very much interested how to open this black box and making or better understand how these models come to their decisions. And in a way, model interpretability you can also consider as a form of a sustainability issue. But my today's talk is not supposed to be about model interpretability, but rather more about this general notion of model training and the accompanying energy consumption. So for my own research, I came up with these two architectures. Both are like multi-level ensembles of 3D convolutional networks, which I stack together in different layers and then fed them with different MRI sequences. And then the question is now how much energy actually such huge ensembles have. So here we can maybe for now concentrate on the left-hand side to one or the bigger ensemble when it comes to parameters. So here I trained this ensemble with 30 base models. So each of these base models is a 3D convolutional network. And the overall ensemble had then about 55 million parameters. Each base model I trained for 40 epochs. The training time was about more than 2 hours. And this add up then to a total training time of about 72 hours for the whole ensemble. So, and then this whole ensembles, then I had in two configurations. So these two types I had then again in two configurations. So the total training times you must then multiply by 2, and then you reach almost 1,740 hours of training time. And then there's this nice platform or website, greenalgorithms.org, where you can plug in basically this training time in combination with the hardware you used. And this gives you then this estimate of energy consumption and translates it also in potential your carbon footprint or the carbon footprint of your model. And equivalence, for example, in terms of flight distances. And this is quite substantial when you think about our previous talk, where we learned that especially air travel to conferences and so on is a major contributor of the CO2 budget of individual researchers. And Even though here it's just a flight between Paris and London, it's still quite substantial. So the big question is now, knowing that these models have these predictive capacities, how to make them also more sustainable for neuroscientific research. And the sustainability topic is not only about the computational time, but also the engineering work which flows into that. I spent really a lot of my time in fine-tuning and the architecture and the setup, which should not be neglected. But one big benefit of these models is that they're quite generalizable, especially when you compare that to other approaches. And this generalizability is something we can use for making the usage of these models more sustainable. And here the central goals would be to recycle models and in the same time make them also more easily applicable. So basically provide them to the community such that we can share basically the used training time and engineering work with each other. And alluding to this idea of open science and open source. The concept of transfer learning as a form of model recycling is actually quite old. So there was already, for example, the paper in the field of computer science by Trun from 1995, who discussed the idea of lifelong learning, but also learning on many tasks and how this can basically benefit and be data efficient. But also after the big rise of deep learning models, this concept was picked up again. And for example, Usinski et al. Could show that even when you use these learned features to a very distant task, this is even better than starting or learning a model from scratch. And this is basically depicted here on the right hand side in this schema, where you can see that a transfer learning model basically would ideally start with a higher performance in the beginning of the training process. It has a steeper learning curve, and then in the best case also has an ultimately like a better performance than a model which is initiated fresh. And in the field of neuroimaging, medical imaging, this is actually something you see already a lot. So there are many papers who report using transfer learning of models which are initially trained on naturalistic images like ImageNet, and then use these models for medical data, where we often have the case that data is sparse, especially when you think about pathologies. And they report also quite a success with this approach. So for example, Ding et al. From 2018, they used this for Alzheimer detection from MRI. But there was also a more systematic analysis of this approach by Rauge et al., what they found is that the performance gain in the end is not very big, even though I have to say that they also trained these models for a long time. So in the end, they basically converged to the similar performance. However, the slope or the steepness of the learning curve was higher, also in their case, for these transferred models. So also to give you a visual idea of how this works. So consider here, for example, in the top row, like a model which is trained on a large MRI data set, for example, brain age estimations, which is a regression problem. You can then take part of the model, where you usually take rather the first layers of the model, and then transfer it to a smaller data set. And this can be then also done to a new task, for example, the classification of a certain disease and so on. And what you usually do is then, as I said, you take the weights of the previous models and then basically just cut off the upper part of the model and then basically stack a new fresh submodel on top of it, which you then train. Obviously, there are also different flavors to transfer learning, and it depends a bit on the distance to the new task, also how similar the new data set is, what kind of transfer learning approach is more applicable. Next, I want to introduce, or at least more propose, a bit more speculative idea, which I think would be also nice to discuss here. And this also picks up some of the ideas which of the paper by Trun, namely the idea of a lifelong learning big shared neural network. So the idea would be to have like a large scale network which is shared among the neuroimaging community, and which could be even called the deep neuroscientist or so. And the idea would be to train this model to become a form of a new SPM or other MRI preprocessing tool. And this very much alludes also to this concept, which was introduced in a very exciting blog post by Andrew Carpathy in 2017, who termed this idea software 2.0. So the idea is, rather than in the kind of classical software where you basically hard code everything, that you rather prompt or state an optimization problem to a big neural network, and basically give it just the data in order that the network basically finds the right software to tackle the issue. And in the same time, this could also benefit an old problem in the field, namely sharing data. So there's often, especially with medical data, this privacy concerns, and models can be shared, whereas data often can't be shared. And ultimately, to also pick up what Evelyn already introduced briefly, I think this all comes with the general idea, or is under this general umbrella of open science. And in this recent paper, which we wrote together with Gisela Hofmann, we argue that there are many sustainability arguments also for open science. So how could this look like with this large-scale network which is shared? One way would be to train this on the existing big open data sets. And there's also previous research which could show that at least in the same task, these networks also nicely generalize to new data sets. And then you have basically this big trained large-scale neural network on a public online server, where individual scientists can then download this model, who have their own little new data set, and then they use the model for that, and then train the model maybe a bit further, and then upload this upgraded model back to the cloud. And in a form of validation step, the network can be then basically validated on previous data sets in a distributed fashion, and with this one could basically compute or basically accept or adapt or decline a certain upgrade of a model. And ultimately you not only have then obviously one model, but maybe you also have a history of previous models which could be revisited. So as a summary, I think after all these years of model explosion and exploration, I think maybe it's time for consolidation. Transfer learning could makes these models more reusable. There's definitely the need for establishing good guidelines and heuristics how to use transfer learning techniques. And then, as I just introduced, also this idea of basically nurturing like a large-scale model together as a community. I think this maybe also alludes to this, what Nano de Freitas recently posted on Twitter, where he said basically it's all about scale now. So this might sound in the first place very unsustainable, but ultimately this could lead also to more replicable and reproducible research workflows. And ultimately could be also then more sustainable than when we think about more the status quo of having basically too many pipelines which are offline and often not shared. And with this, I want to thank you for your attention, and I'm very excited already about the discussion.